Welcome to the SciFeed Guest Show, a podcast where I talk to different scientists about the work that they've done and the topics they know best. In this episode, my guest is Simon Clark, who gained a PhD from the University of Exeter in atmospheric physics, and we talk about the atmosphere, global warming, and Simon helps to explain some questionable science facts that I found online. Thanks for coming onto the podcast, and to start off, could you tell us a little bit about yourself?
Sure. So I'm kind of an unusual case of an academic leaving the system and continuing to talk about academia, but in sort of communication side of things. So I did my PhD at Exeter University, and before that I studied physics. And during both of those degrees actually, but mostly during the PhD, I discovered that I really enjoyed doing communication and making videos specifically. And so when it came to graduation, I decided that I wasn't expecting to be able to do it full time, but I thought I would regret not giving it a shot. And so I went full time making videos and doing a podcast and live streaming. And since then, it's somehow worked out that I've been able to do it full time. So I mostly focus on videos about science, although there's been a whole variety of stuff that I do now. In terms of Twitch streaming, I do a science stream on Wednesdays, but then I also we're recording this on a Friday. After this, in the afternoon, I'm doing a Warhammer painting stream. So it's interesting that it's sprawled into my other interests. But yeah, primarily on YouTube, it's science and specifically climate science, looking at how the atmosphere behaves and what we're doing to it, basically.
And during your PhD, was it the stratosphere that you were looking at?
Yeah, so the Earth's atmosphere is like ogres, it's like onions, it's got different layers. And basically, we live in the lowest layer, the troposphere. And the layer above that, the stratosphere, is obviously a lot lighter than the troposphere, but it extends from about 10 kilometers to 50 kilometers above the surface, so it's got quite a large extent. And for the longest time, it was believed that because of its low mass, it just didn't have a huge influence on the weather. And it was only in the mid-50s, really, that its influence was identified as, it has an influence the whole time, but the most extreme form is something called a sudden stratospheric warming. Which is an event where effectively the stratospheric polar vortex, which forms every winter in the high latitude regions, which is just a big sort of spinning donut of air. It spins at hundreds of kilometers per hour, 200 kilometers per hour. It's the size of North America. It's huge. And then about 6 times every decade on average, it just tears itself apart. And we have some idea as to why, although not the most pleasing explanation exactly for, in terms of physical intuition. But what we really don't have much of an idea of is how it communicates its influence to the surface. We know that it does. My supervisor in my PhD wrote a paper about 20 years ago, which showed that there is a definite downward influence of these events on the weather, and specifically things like changing storm tracks and having cold air spilling further south. In the UK, we had the beast from the east a couple of years ago. There was also, I think it was either last year or 2 years ago, there was a huge outbreak of cold air over North America when, Chicago was colder than the South Pole at one point as a direct result of these events. And we know that it happens, but we don't exactly know how it happens. So that was what my PhD was about. It was about coupling of the stratosphere and troposphere and testing a specific hypothesis that we came up with, my supervisor and I, which kind of worked, but not really. If I was to do it again, I would do a lot of things differently.
I guess it never quite goes to plan.
No plan survives contact with reality. And it's definitely true in academia. I mean, I feel like there's this conception that people have of science and of research being, you have an idea, you execute the idea. If your idea is good enough, you get a Nobel Prize. And it's not really like that. It's more of a meandering, kind of ball of string, and it's just a tangled mess. And, you go down these dead ends that you think are a good idea, but actually that for whatever reason don't work, which could be because it was a bad idea, or it could be a technical reason, like you're not good enough at programming, or you don't have the resources to be able to try an idea. And it's definitely not a linear process. It's always adapting on the fly, and also, frankly, adapting to what you can practically do in terms of what you're funding. You have the time to do, what resources you have available, and also, how good your supervisor is at supervising. They always tell you in training that a supervisor is like a little tugboat. You're a big ship coming into harbour, and the supervisor is a tugboat. You're providing the bulk of what's going on, but the tugboat can nudge you in the right direction. And some supervisors are very good at that. Some supervisors are basically just like drunk at the wheel and don't provide you with very useful nudges. So there's so many factors that go into, how successfully your plan is enacted. I'm sure that there is probably one PhD out there who is listening to all this and thinking, well, my plan went perfectly. I had a plan and I executed it. And
yeah, there has to be some who's going really well.
Yeah, there's an exception that proves the rule, But for the most part, yeah, science is a case of compromise and improvisation.
You said just before, when you were talking about this sort of donut of wind splitting, there was a not very satisfactory explanation to physicists.
Yeah, so we have this since the 70s. I think the Matsuno paper was 71. We've had this explanation of wave breaking. So basically, the polar vortex is formed by a temperature difference between the equator and the pole. So obviously, the equator is warmer than the pole, and a combination of the temperature gradient with what's called hydrostatic balance, which basically determines how density changes as you get higher in the atmosphere. Those two together form a phenomenon called the thermal wind, which is basically a wind shear. So the wind gets stronger as you get higher. So because there's a temperature gradient from the equator to the pole, and because it's higher up in the atmosphere, you get very strong winds. The break on that is this wave breaking. So you get atmospheric waves, which can be literally the size of the whole planet. We can sort of define waves based on their wave number, which is how many times their wavelength fits around the globe. And so a wave can be one hemisphere being slightly lower pressure and the other hemisphere being slightly higher pressure, or it can be, higher wave number. And what happens is you get these waves that will propagate around the Earth west to east, and also from vertically from the surface going upwards. And they basically reach a point in the atmosphere where they will break, much like ocean waves will break when they reach a shallow enough part of the ocean close to the shore, and they deposit their momentum. And so, much as those ocean waves will deposit their momentum and push material up the beach, these waves in the atmosphere deposit their momentum, and they do it in such a way that they slow the polar vortex. And basically, what happens is, when I say it's physically unsatisfying because I personally just struggle to really imagine it, that you get this wave breaking will happen to a point where it's almost like, I like to imagine it like the brake on a bike wheel. If you apply too much braking, eventually the bike wheel will stop. And that will happen at a high level, so goes the theory, in the atmosphere. And because of a peculiarity of how these waves propagate through the atmosphere, when you have dead air that isn't moving, the waves can't propagate anymore. So what happens is you get this layer where suddenly there is no vortex anymore. Sorry, for those of you who are listening at home, I'm doing hand gestures as if that's somehow helpful for a podcast.
But it's almost like the air gets so thick it breaks against it.
Well, it's not so much that it gets so thick. It's just that the flow characteristics, rather than the density, it's how it's moving. And if you get this air that isn't moving zonally, which is to say east to west or west to east, then it breaks. It can't propagate anymore. And so you get this surface that starts in the upper atmosphere, and then as more and more waves break and causes more and more breaking on the vortex, it starts descending through the atmosphere. And that mathematically, it's a lovely solution to it. And I think it's something that you learn relatively early on in the process. But after however many years, I still don't find that satisfactory. I don't find that a particularly nice way of thinking about why this phenomenon happens. I mean, in the thesis, we invented this idea of mass fluxes. So instead of considering wave breaking, you basically just draw a cylinder, you draw a circle on the ground over the Arctic Circle, and then you create a cylinder vertically above that, and you just consider how mass flows into and out of that cylinder. And the way that we conceived it was very much the air masses at the top you basically get air being pushed in at the top, and then that squishes down on the column and causes all the sort of knock-on effects. But fundamentally, it's something that's very difficult to visualize because it's thin air. It's something that is fundamentally not got. It's intangible, and particularly when you're talking about the top of the stratosphere, the air pressure there is about between 100th and 1,000th what it is at the surface. So it's invisible, clear air, and there's much, much less of it than you're used to at the surface. So it's basically, you have to rely on these mathematical models. So perhaps we're doomed to not actually have a physically satisfying explanation of it because it's a very physically unsatisfying system in the first place.
Yeah, it's not really easily imaginable how it can kind of squish everything down.
All these meteorologists in the lower atmosphere who deal with things like hurricanes and tornadoes, they can see what's going on. You know, there's moisture that can form clouds, and it's thick and goopy air that has like a lot of momentum to it. Whereas us stratospheric dynamicists, we had to use our imaginations. It also meant that I didn't get any cool opportunities to do field work in the PhD. I have friends who got to go off if they were investigating the monsoon. They did a placement in India, flying planes through, monsoon clouds or investigating hurricanes or whatnot. There's no way I could go and have a look at the polar vortex. It's just...
Yeah, no free holidays flying into vortexes.
Unfortunately not.
Although, it would be quite an adventure to go that high up.
Yeah, I was doing some research on this quite recently, actually, for a video project. The people who first entered the stratosphere were these balloonists in the mid-19th century who nearly died doing so because they basically ascended a lot quicker than they thought that they would, and they got completely caught out by the lack of oxygen and how cold it was. And so reading about this adventure they had, it was Cox and Glacier, just makes me think, maybe I wouldn't want to go up, I mean, obviously technology is a lot better now, and we'd be aware of what we're getting into, but it's not necessarily the most appealing.
I don't know, when you're thinking about you're just flying up in a balloon of air, it still doesn't feel like it would be very technologically advanced.
Yeah, but I mean, they didn't have oxygen. They also were wearing, they took off from Wolverhampton and landed in a field near Shropshire. So it's not like we're talking about these guys wearing like woolen mittens and not space age, incredibly padded suits. But I don't know. It might, if anybody listening to this wants to sponsor me to go up to the stratosphere for a video, I'd listen. Let's put it like that. As long as you can protect me properly.
Is it actually possible to get high up in a balloon without damaging yourself?
Yeah, definitely. Well, I mean, Felix Baumgartner jumped from, I think he would have been the upper stratosphere. I can't remember off the top of my head what his record altitude was. I mean, the record balloon altitude off the top of my head, it isn't manned, but they got up there with a balloon, was I think 53 kilometers. They just about peaked into the mesosphere, which is the layer above. But you can go up into the stratosphere, but you would definitely need oxygen and you would need thermal insulation, because the temperature at the bottom of because the thing about the, probably should have said this earlier, the interesting thing about the stratosphere is that compared to the troposphere, our layer of the atmosphere, obviously in our layer of the atmosphere it gets cooler the higher you get. That's because the Earth is heated, so the Earth's atmosphere is heated by the Earth from underneath. But you might think of it as being heated from the sun, but the atmosphere is basically transparent to most of the sun's radiation, and instead that goes straight through to the Earth, which then re-emits it at longer wavelengths, which do get absorbed by the atmosphere. So it's like the atmosphere is heated from below by a pan rather than a grill. And what that means is that our layer of the atmosphere gets cold as you get higher up. But that reaches a certain point at the top of the troposphere where it then stays the same temperature for a bit as you get higher, and then it actually increases in temperature as you get higher. And that's because of ozone in the stratosphere, which absorbs ultraviolet radiation from the sun. So you get this heating source from above. So the atmosphere actually then gets warmer as you get higher. So I think the boundary at the top of the stratosphere, it's about 0 degrees Celsius, roughly. Whereas at the bottom, I want to say it's about negative 60 Celsius. So it's really quite cold. I mean, in the lower of the stratosphere, where feasibly you would be going, it's perishingly cold. But, that's about Antarctica temperatures, really. But you also have to worry about oxygen. So, you can get up there, and you wouldn't want to stay up there for terribly long necessarily. But it is very possible to convey yourself by balloon, and it is possible to survive.
You need more than mittens.
Yeah, you need more than woolen mittens and a sense of Victorian stiff upper lip.
Between each layer, is there quite an obvious boundary, or are there kind of layers within layers?
So, I used to think that it was quite, because you wouldn't think of there being, the atmosphere just gets thinner as you get higher up, and so you think of it, there would be some kind of fuzzy boundary. But I actually did, I filmed a weather balloon launch at Reading a couple of years ago, and we were looking at the data in real time, and it's actually quite striking. When you go from the troposphere to the stratosphere, it's just like it flatlines, basically. It's a really sharp gradient. And that's because so much of what makes the stratosphere interesting is that vertical temperature profile of it getting warmer as you get higher. And that's just something that once you hit that boundary of, well, originally it's isothermal, meaning it's the same temperature as you get higher. that just immediately has an impact on the dynamics. So at a given instant, it is quite a sharp boundary. But then when you take an average over time, if you take an average over, say, an entire year, it then becomes very fuzzy because the height of the tropopause, which is the boundary between the two, varies quite a bit, just depending on atmospheric conditions. But at a snapshot, it is actually a very sharp boundary, which is kind of counterintuitive.
It's always moving throughout the year, but when it's fixed, it's quite specific.
Mm.
So what layer is it where you're officially out of the Earth and into space?
No, that's something else I've been writing about recently. There is no one start to space, because the thing about the atmosphere is that it is just this exponential decrease of gas. As you get higher and higher, there's just increasingly less of it. So at some point, you have to make a cutoff. Historically, and there is actually a pretty reasonable explanation for why, there is the International Start of Space, which is the Kármán line, 100 kilometers, which is basically approximately the height at which an aircraft can, using lift, fly in a non-straight line, as in it can not just follow the contours of the Earth. In other words, it's not in orbit. That's basically the maximum altitude that an aircraft can do that, which is actually about 96, 97 kilometers, I think. So they rounded it up to 100 because it's just a nicer number. And so there is a certain physical justification for that, but that's very much like a human way of looking at it. If you want a more kind of physical definition for the top of the atmosphere, there are a couple of candidates. You've got the top of the, I've got to get this the right way around now, because I certainly don't look at the upper atmosphere very much. I'm much more of a middle atmosphere kind of guy. But the top of the thermosphere is the point at which there are gas molecules around, and the pressure is something like a millionth what it is at the surface. I can't remember off the top of my head. There are gas molecules around, but they don't behave as a gas. There's not enough of them to actually behave in a way that we would recognize as a gas, and so they're kind of just a soup of molecules. And so that's quite a reasonable place to argue that that's the top of the atmosphere. Alternatively, you could go to the top of the exosphere. So that, for reference, is at about 600 kilometers.
A lot higher then.
Yeah, I mean, it's so high that the International Space Station is orbiting within the thermosphere. It's, it goes from about 80 or 100 kilometers roughly to about 600 kilometers. So it's a big chunk of the atmosphere. But still, when you think about how big the Earth is, the Earth's radius is about 6,400 kilometers. So it's still really quite a small addition to the Earth. Practically, you could say you would recognize yourself as not really being in the atmosphere anymore from probably the stratosphere, the top of the stratosphere upwards, which is 50 kilometers. And there's analogy is that if you have a globe, like a typical football kind of size globe, and the atmosphere would then be as thick as roughly a layer of varnish that you were to put on top of it. So it's really thin compared to the size of the Earth. But if you wanted to go the whole hog in terms of what you could conceivably call the atmosphere, there's the top of the exosphere, which is basically where the radiation from the sun has a greater pressure, a greater force exerted on the molecules of the gas than the Earth provides via its gravitational pull. So that's the point at which the atmosphere is truly being stripped off by the solar wind. And that can be as far as 10,000 kilometers. It can actually be even further than that, actually. I think it's been recorded as up to several 100,000 kilometers. So, the moon passes through, in the lee side, if you like, of the Earth, can pass through what is technically the atmosphere. It's good. It's got a wonderful name. It's called the geocorona, this kind of halo of atmosphere that still just about surrounds the Earth.
Just there on the edge.
Yeah, I mean, you wouldn't recognize it as being an atmosphere. I think practically 100 kilometers is fine. It's a fine definition. But, if you're being properly academic about it, the top of the thermosphere would probably be the best place to be, because I would define the atmosphere as being, yes, there are molecules of oxygen, nitrogen, although actually at that height it's mostly hydrogen, but they're a gas. The atmosphere is a gas, and once it stops behaving as a gas, it's not the atmosphere anymore. So I'd say really about 600 kilometers.
So going back to the part that you study, the stratosphere, what sort of big effects is that going to have with climate change?
So it's an interesting question, because you'd think that one of the consequences of climate change is that the equator to pole temperature gradient is going to be lessened, because climate change is, rather, anthropogenic warming is occurring at a faster rate at the poles than at the equator. For a variety of reasons. It's to do with poleward mass heat flux. So, we're intensifying the circulation that draws heat away from the tropics towards the poles, but also things like feedback cycles, like ice is melting over the poles, and so the albedo, how much of the sunlight is being reflected, is being lowered. So, when you replace ice with ocean, suddenly you're heating that area more. So that temperature gradient is being lessened, which you would think would weaken the jet stream, it would weaken the polar vortex. But so far, it's still unclear, was probably the best way of putting it. I think most of the evidence would come down on the side of the polar vortex's influence on the weather not actually changing very much. In various model runs that have been done, there haven't been an increase in the number of sudden stratospheric warmings, which is kind of what you would intuitively expect because the vortex is weaker, so it would be more easy to disrupt by the wave breaking and that transfer of momentum going on. But according to the studies that I've read, most of them at least, because some people do seem to think that it would increase in frequency. Most of their simulations seem to suggest that SSWs won't increase in frequency. That's, of course, only one part of the influence. That's the biggest part of the influence. The stratosphere does have some influence on the weather in other ways, such as there's the QBO, which is the quasi-biennial oscillation, which is just what's the word I'm looking for? It's an alternating pattern of westerly-easterly winds over the equator, basically. And I don't know off the top of my head how that would be affected by climate change, but I would be very surprised if it isn't affected by it. And the phase of the QBO, whether it's east or west, does have an effect on the weather. That's not something that I've researched and looked into the literature for. And I also don't know enough about what the jet stream is going to do in response to it. I believe the jet stream is going to weaken and become more wavy, basically. So you will get these larger variants of temperatures in the mid-latitudes, like in the UK. But that's, again, it is a sort of a top-level assumption based on the basics of what's happening. And I don't know enough about any complications to that to say if it would definitely happen or not.
So I've got a few myths that I've found on the internet that you might be able to find the answer to. Some of them are a bit strange, so I don't know if you will. But I'll start with the first one. I read on an online forum, it wasn't any sort of scientific place, so this could be completely incorrect, that different parts of the atmosphere are cooling even though our atmosphere is warming, and somehow that's going to cancel out climate change.
Yeah, so there's different interpretations to that. I mean, the main thing is that the stratosphere is cooling whilst the troposphere is warming. And that's basically because the troposphere is absorbing more of the radiation. As I kind of said before, the Earth is being heated, the Earth's atmosphere is being heated from below. And so once you add more absorbing stuff, whether that's methane or carbon dioxide or any number of compounds into the atmosphere, it's preventing as much radiation from reaching the upper atmosphere. And so that's going to cause the upper atmosphere to cool whilst the lower atmosphere still warms, which does seem a little bit counterintuitive. You'd kind of expect that the upper atmosphere would also warm at the same time because it's the same system. But it's effectively like placing more shielding almost between the lower and upper atmosphere. What will happen in the end is that the Earth underneath the atmosphere will warm to a point where the upper atmosphere will gradually return to the original temperature. I imagine that would be the end equilibrium state. But certainly in the short term, what you're going to see is that kind of dipole of warming in the lower and cooling in the upper, which I still find a little bit counterintuitive. But yeah, that is what the data suggests.
Okay, so definitely it's not going to cancel out climate change.
No, unfortunately not. A lot of these myths that people say, like, this section of the atmosphere is cooling and so it's going to cancel out the warming, or there's going to be more clouds, which means that there's going to reflect more light and so that's going to cancel out the warming. Believe me, climate scientists would love for these things to be true.
Yeah.
Unfortunately, it's just not what the data suggests is going to happen. I think there are very few people who would love for the climate emergency to not be a thing more than climate scientists. Because, we get into this field because we value the planet and we value our continued existence on it. And so we study it not because we have a sick, morbid fascination with watching our own demise, but because we're invested in it.
Yeah, it's not to make people feel bad, it's actually to try and figure it out a little bit more.
Yeah, and so if there's not a problem anymore, that's an ideal case scenario. That's great. I can now go back to my full-time job of painting Warhammer figures.
The second one I have, and this one might be a little far-fetched, when people think of colonizing Mars, that you could nuclear bomb Mars and create an Earth-like atmosphere. Is there any truth in that, or is that nonsense?
I mean, oh god, it's of all the experiments I've ever heard, I want to try it so much.
Yeah.
I think the idea behind this is that there's an awful lot of CO2 that is trapped in Mars's substrate in the surface in the form of dry ice. And so if you detonate explosives or nukes on the surface, you basically force a lot of that into the atmosphere, which would then kickstart a kind of greenhouse effect. It would be like a short, sharp shock to the system. You suddenly inject all of this stuff into the atmosphere, along with a bunch of dust, which would also reflect sunlight. But I think the net result would be probably a positive greenhouse effect. I don't know if anybody... I remember hearing about this from Elon Musk, and I don't know if any actual studies have been done on it. I don't know if anybody's modelled it. Perhaps that's something I could do. But so I don't think anybody could say for sure if it would definitely work or not. I mean, the other thing is that you would be able to create, let's just say hypothetically that you did detonate nukes and you injected lots of CO2 into the atmosphere, and suddenly you took it beyond a point where there was then a positive feedback cycle and it melted all the rest of the ice and the dry ice, and there was a positive greenhouse gas feedback cycle. That's one problem solved, but Mars is still not suitable for human habitation just on the surface because of a variety of factors. I mean, for one thing, the atmosphere is still almost entirely carbon dioxide. So there is an atmosphere there, but it's something like 1 or 2% the thickness of the Earth's atmosphere at the surface. And it also doesn't have a magnetosphere, so it doesn't have protection from the sun's radiation. The Earth has a spinning molten core, which produces a big dynamo that shields us via the magnet dipole that results from that. It shields us from the sun's radiation, whereas Mars doesn't have that. For whatever reason, its core kind of died. And so you would, hypothetically, you'd be able to stand on the surface with a rebreather, but you wouldn't want to be out there for very long because you'd still have the problem of radiation. So I feel like if any problem is so big that nukes only solve one part of it, it's probably too big of a problem for us to kind of actually attempt.
Yeah, just solves one very small piece of that puzzle then.
And also creates a whole bunch of other problems, like, nuclear fallout just whizzing around the atmosphere.
Yeah, not the nicest place to live, really. Another one is, do ozone holes just appear and disappear by themselves?
Yeah, so the ozone in the atmosphere is controlled by what's called the Chapman cycle. So basically, ozone forms when you get oxygen is normally diatomic oxygen, so you get two oxygen atoms in a molecule. And what happens is certain wavelengths of the sun's light will break apart that molecule, and you'll be left with two single oxygen atoms. Most of the time, they'll just recombine and form diatomic oxygen again, but sometimes it will combine with a pre-existing oxygen molecule and form ozone. So you have three oxygen atoms in a row. And what happens then is that molecule can be broken apart by ultraviolet radiation, and you get this kind of cycle of monatomic, diatomic, and triatomic oxygen that kind of just interact with each other in balance. And the balance of where the specific wavelengths of radiation are kind of present in the atmosphere because they haven't already been absorbed means that the concentration of ozone is just way highest in the stratosphere. Now, what you can do is introduce another chemical element which will bind to the ozone and basically remove it from the system. And that's what CFCs were. So chlorofluorocarbons, which were used in coolants in fridges and in hairsprays and stuff like that, basically were an extra sink on that system. And so the presence of CFCs in the atmosphere disrupted that equilibrium. Now, because of how atmospheric circulation just so happened to work, the ozone is concentrated in the over the poles, and over the South Pole was where the ozone hole was originally sort of identified. And that's also where the CFCs have been sort of accumulating. So the ozone hole was definitely created by us. Where the ozone was already there, the ozone hole was created by us because we injected all these chemicals into the atmosphere that disrupted that equilibrium. And the reason that it's healing is because we stopped emitting CFCs, basically. The Montreal Protocol in the 80s stopped emissions, although there have been quite a lot of emissions from China in the past couple of years, which are definitely against international law. Quite what we're going to do about that, I don't know. I'm not a politician.
Yeah, difficult one.
Yeah. But the reason that it's been healing hasn't just been spontaneous. It's because we've controlled the concentration of those CFCs. And I think the latest estimate I heard was that by the middle of this century, it'll be back to pre-industrial kind of concentrations of ozone. So as long as we stop, we at least we control the emissions of these chemicals, really it should kind of be healed before too long. So it definitely doesn't just ozone concentrations are whisked around by the circulation in the stratosphere anyway, but they don't, the holes like we see talked about in the press don't just appear and spontaneously disappear. They definitely appear because of human action. They only disappear because we take positive action to prevent the cause.
And is there any reason why there's like a larger one, I think, over Australia rather than just small ones scattered around the planet?
So I haven't looked at the exact. This is basically tracing of particulates in the stratosphere. My guess would be that it's because the southern polar vortex, the austral polar vortex, is a lot stronger than the northern polar vortex. So it's going to entrain and trap more ozone over the South Pole, because you're dealing with the circulation. It's about 300 kilometers per hour in the southern hemisphere in the winter, and so it's basically constraining all the ozone to be an area just over Antarctica, which does vary a little bit. So sometimes it can be over Australia or New Zealand or what have you, but basically just over Antarctica. And I think just because of the magnitude, the strength of that circulation is so much greater, it produces a more pronounced, more concentrated effect.
So it's kind of just all about the speeds and the difference in the patterns.
Yeah, I think it's basically the circulation pattern being different, which is different in the southern hemisphere because there's so much less mass, land mass in the southern hemisphere. It's sort of bizarre, but if you flip a world map upside down, you realize just how empty the southern hemisphere is. The northern hemisphere is chock-block full of land. Southern hemisphere, not quite so much. And so there's less land-sea contrast, which produces fewer of those waves that propagate up and break in the atmosphere. And so effectively, you've got less of a break on the vortex in the southern hemisphere, which is why it's so much stronger.
So that's kind of the end of the myths, but I wanted to ask if there's any area of science, if you were to go back into full-time research, that you would really want to learn about?
Oh boy, I'm one of these people. I'm academically omnivorous. I just can't help but find stuff interesting. I think something that I have done a little bit of since leaving academia, and I'd be really curious to try and apply, is doing some machine learning stuff. So I experimented with doing a couple of machine learning based videos, which were fun, and also just a complete dark art. What I've learned is that machine learning is like witchcraft, and it's more an art than a science, really. And I feel like I would be really interested in going back and applying machine learning techniques to something like classifying southern stratospheric warmings. But also something that has been really interesting has been community action on climate change. Both community communication in terms of what I do on YouTube and whatnot, but also the mass projects of combining people together to, for example, do distributed computing to do climate modeling. And there's something to do with the interaction of communities and climate science I would find fascinating. I'm not against going back to academia, but I feel like when I finished the PhD, I was definitely done for a good while. I definitely wanted to step back for a bit because I just wasn't enjoying it, and I was enjoying doing the communication side of things much more. So if I could combine communication with the actual academic, the atmospheric physics side of things, or just full on kind of science communication, because there are departments that do that and research it, I would be interested in going back.
On the community climate change front, do you know much about I think it's called the Great Green Wall in Africa, where they're trying to plant lots of trees along a desert border?
No, I mean there are a few sort of big projects like that are the afforestation side of things, which I did a video on Team Trees, which definitely pissed off a lot of people. But the problem is that a lot of the action on climate change comes down to the individual, or the onus is put onto the individual, which is only one half of the puzzle. And I feel like the whole reason I did the video on Team Trees was that people seem to think that by planting 1 or 2 trees, they've somehow wiped out their contribution to global warming. And actually, it's not enough. Yes, it's a positive action. I'm not disputing that at all. But if you plant, if you plant 20 trees, it's the equivalent of the greenhouse gas drawdown, is the equivalent of the savings in emissions from being vegan for something like 2 or 3 years. It's the impacts that you can make by other individual actions are much, much greater. But the far bigger problem is that it ignores the contribution that governments and corporations have, the role that they can have in limiting emissions. I've done a fair bit of work with the Renewable Energy Network, who are based in Paris at the UN site. And they produce this report every year that isn't so much focused on the technology of renewable energy, which is a part of it, and they're looking at installations of new tech all over the world. A lot of it is policy. It's looking at what governments have got a policy that says we aim to have this amount of energy being generated by renewables by this date, and breaking that down by electricity generation, by energy use in transport, and energy use in heating and cooling of homes. Because electricity generation is, off the top of my head, about a quarter of energy use. The rest of it is transport, and the vast majority of it is energy for heating and cooling. So air conditioning, heating of homes. So in the UK, using gas to heat our homes, for example. And these are areas that really individuals can make an impact. But really, it comes down to governments and also corporations. Like with a huge number of big corporations, like Amazon, Google, Apple, Samsung, wherever, if they were to change their behaviors, that's so much more effective than putting the emphasis on the individual, which is it's quite a neoliberal concept anyway, of this responsibility being on the individual, not on the state, that's when you start to get into like the really clever people who talk about politics and what the right actions, what the right distribution of actions are between the individual and governments. But those kind of projects, they are doing good. I think the problem is that they're a little bit like a band-aid on a broken leg. It looks like you're doing a good thing, but it's kind of not addressing the problem at a scale and in a manner that is appropriate to the problem at hand.
Yeah, it almost distracts from the big thing that you could do.
Yeah, it's imagine if someone like Jeff Bezos were to donate $1 million to help the living conditions of his employees. It's like, yeah, that's a good thing, but you're the one who's created those living conditions and you're not paying them enough,
Yeah, it does seem like larger organisations would have the power to do more than one person. Are there any single things that an individual can do to improve the environment?
Yeah, I mean, the single biggest thing impact you can have on the climate is to not have children. But that's something that we don't talk about for a variety of reasons, because it basically strikes at the fundamental thing that makes us human, our desire to procreate. And, there's something fundamentally ethically icky about telling people not to have children. So putting that to one side, the biggest actions are really lifestyle dependent, of course. For the average person, flying less, particularly if you live in somewhere like America where people fly domestically a lot more, and domestic flights are worse than international flights because the fuel efficiency is a lot lower, because they spend a lot more of the flight at lower altitudes where there's more resistance, and they jetliners on international flights will fly in the stratosphere because there's less air turbulence and because there's less resistance, so the fuel economy is better. So flying less and changing your diet. Vegan is definitely the best, though if you cut out meat, frankly, if you cut out beef from your diet, if you cut out any form of meat from a cow, you're already having a huge impact. I did a video relatively recently on how much of an impact food miles have, because I think there's this idea that people have of, well, I eat meat, but it comes from local farms. And transport on average accounts for some less than 10% of the total greenhouse gas emissions of a food. For beef, it's like 0.5%. It's almost entirely how you change the lands to accommodate the livestock, but also what you feed the livestock and also processing it. The actual and you can do a comparison by calorie and by kilogram of food, and beef is by far the worst on every measure. So if you cut that out, then you're already having an impact. If you cut out all meat, you're doing a really good thing, and then if you cut out dairy, you're also substantially lowering your individual footprint. But similarly, it's a big ask to ask people to go vegan. I'm vegan about half the time. I'm vegetarian the other half of the time. And at the end of the day, it's not about going cold, well, quite literally cold turkey. It's about limiting your emissions, limiting your impact. So it doesn't have to be an all or nothing. And it'll be interesting. There have been studies that have looked at the impacts of changing diet like this, and it also depends, of course, on where you live and what the rest of your diet looks like. There was a study that I linked to in the video about looking at the average EU diet, and I think it was something like, if you cut out all meat and dairy, you'd reduce the average person in the EU's carbon impact, food carbon footprint, by something like 70%. It's basically diet and transport are the two big things, and then frankly voting as an individual action, campaigning for people in government and also in corporations to take those large scale policy decisions to commit to energy targets in heating and cooling and in transport. That's an individual action, but it has ramifications on a much larger scale. So if there's a single thing that you can do, it is voting, followed by flying and changing your diet.
For anyone who is listening who wants to learn more about the work that Simon does in any of these topics, he does have a YouTube channel, which if you just search Simon Clark is probably the best way.
Yeah, I regret the username. It's Simon Oxphys, but there's an F. It's because I did physics at Oxford, and Simon Oxford Physics made sense at the time, but I put an F in the middle of it, so just search Simon Clark.
That makes sense. And as a final question, for anyone who wants to get into physics, or even people who don't necessarily want to work and research in it, where would you recommend they learn more aside from your own channel?
Oh, blimey. There's a huge amount of stuff that's available on YouTube. Basically, any topic that you find interesting, there is somebody out there making good videos about it. If you wanted something more formal, I guess, well, there's nothing stopping you from just, if you find something interesting, and I never did this as a kid, one of my biggest weaknesses as a person is I don't change the environment I find myself in. I just adapt. I didn't, for example, as a kid, just buy a physics textbook and start learning it on my own. I didn't have the idea to do that. And there's nothing stopping people from, I've done videos recommending physics textbooks, and if you're at high school or GCSE and you'd like to, just get ahead of the game, there are textbooks you can buy and just work through. Or if you want to do it online, there are services. A long-term sponsor of my channel has been brilliant.org, who obviously I'm biased because they have paid me to sponsor them, to advertise them in the past, but they're genuinely really good. And that's all about learning by doing and solving problems. And I had coronavirus recently, and I kept myself sane by doing their chemistry course every day, because I hadn't done chemistry since I was about 16. And that was just really fun, and it was a really good resource. So, you don't have to spend money on it. If you don't want to get a textbook, or if you don't want to get a service like Brilliant, there are plenty of things that are available for free online. Just ask yourself, what do you find interesting, and then pursue it. Fall down that rabbit hole.
Well, thank you to Simon for doing this episode, and if you want to hear more from the SciFeed podcast, please keep an eye on our Twitter and Facebook pages, or keep track of us using your podcast provider. For next week's episode, Dr. Michaela Johnson will be telling us more about paleontology and her field studying fossil crocodile morphs.